When it comes to computer networks in an HPC system, there are two hardware components that you need to know about right now. The first is the connection management device, and the second is the connection medium. In this image of the Stampede HPC from TAC, the Texas Advanced Computing Center, I've only highlighted the components in the two central racks, but all the racks share similar components. Also, the highlighted connection media are intentionally two different colors. That's the orange cables and the yellow cables, because there are two different types of connection medium. What is not highlighted and not so obvious are these black cables with the blue connections at the end. That is another connection medium. The Stampede rack has 40 nodes per rack, and it may not be quite that obvious, but each node has at least 2 network cables running out of them. So that means each rack has at least 80 network cables, needing 80 network ports per rack. Now, the connection management device that is most prevalent in an HPC system is a network switch. And a network switch is a device that centralizes communications among several connected devices in one local area network. And it typically operates on a layer 2, but also sometimes a layer 3 of the OSI model. In plain English, a network switch connects things together. A hub, on the other hand, can be considered a fairly dumb type of switch. While a switch can send data to a specific target using unicast or multicast, a hub sends data to everyone as a broadcast. And both a hub and a switch have a very local view of the network, and they cannot see beyond their network borders, while a router is able to join two separate networks together through gateways to talk to one another. There are many roles that switches can perform in an HPC or cluster environment, but for most HPC systems, there will be fairly simple devices whose primary job is just to connect the nodes together. And there's no better example of this than the illustration of the TAC floor plan for the Ranger HPC system, with its 16 kilometers of network cables all meeting at the center of the data center, where the two Magnum switches resided, with a combined total of over 7,000 network ports for this entire HPC system. Of course, in this example, I might be somewhat oversimplifying the role of those two Magnum switches, but the general concept I'm referring to holds. The switch's main job in your context will be to connect all the nodes of your cluster together. In a later chapter on hardware, you will learn how to identify what features a switch has, as well as how to decide which switch to select for your system design. For now, it's enough to understand that there is actually a difference between a layer 2 switch and a layer 3 switch, and you should be able to understand their fundamental differences by referring to the OSI model. When you go into a sophisticated network infrastructure, there will actually be an assortment of cables, speeds, switch hardware, and connectors, and this heterogeneity is by no means an accident. And having a solid understanding of how the actual network protocols work, in particular a useful understanding of the TCP/IP stack, can help you to optimize your network to account for congestion control, TCP incast problems, buffer bottlenecks, and so on. At the very high end, you will find managed switches that support a range of advanced features, including SNMP monitoring, link aggregation, quality of service support, and software-defined network behavior, which basically means that you can code your network to dynamically react to the real-time status of your network, such as a failed node, congestion on a route, and so on. Like the network management devices, there are also many different types of cables for networks. For now, you will only need to know about two types, Ethernet and InfiniBand. Again, we'll go into a little further detail in a later chapter about the actual interfaces that these devices can use. Ethernet is the most common and well-known of the two. It's an RJ45 cable, and it's what most home networks use. Ethernet performance and capability is defined by what category of cable it is using, and for now it's sufficient to know that Cat5 goes up to 1 gigabits per second, and that Cat6 is up to 10 gigabits per second. While Ethernet is the cheaper option between itself and InfiniBand, it comes at the price of higher latency, which is typically measured in milliseconds. That is 1/1000th of a second. InfiniBand, on the other hand, is a low latency connection. We're measuring that in less than 1 microsecond. That is 1/1,000,000th of a second. So for those a bit weak on maths, it's up to 1,000 times better latency than Ethernet. And the Stampede FDR InfiniBand goes up to 56 gigabits per second, while EDR goes up to 100 gigabits per second, and you even get faster technologies, HDR, NDR, and XDR. In my mind, a really interesting scenario at high-end HPC centers is the problem that arises from having things going just a little too fast. In networking, TCP incast is a classic problem of this phenomenon, but it's an example of the problems that arise when you shift from a consumer level environment to a bleeding edge enterprise environment where you're pushing high performance. What the problem describes is that you have many devices sending data at a very optimal speed to a central receiving point that cannot cope with the workload. All the sending devices detect that there's congestion, and they may back off for a very minute fraction of a second, but all those nested delays of backing off eventually add up, and the throughput at the end suffers to the extent where you sometimes get approximately 10% of the total link capacity actually being used.